Hello, here's another couple of questions on astronomy and cosmology. So we're kicking off with one estimate of the age of the universe is 13.7 times 10 to the 9 years. Calculate the Hubble constant in kilometers per second per megaparsec using this age. And they've given us the number of meters in a parsec. Right, I find people are often not very comfortable with a Hubble constant, mainly because of these weird units, this kilometers per second per megaparsec, where we've got some distance divided by another distance, and then this seconds to the -1 in the middle. So I might dig into this. Actually, I will dig into this in a little bit more detail to try and unravel some of this. Just reading ahead to the second part of the question here to see if that's going to help. Yeah, we're doing a calculation in the second part of the question based on a galaxy which is 50 megaparsecs away. So we're going to be using the outcome of the first part of the question in the second part of the question. So that is going to help. So let's dig into this in more detail then and try and unravel any difficulties people might have. Right, so when it comes to Hubble's law, people are usually happy with the first parts of it. So we've got that V is proportional to D. This is our recessional velocity of galaxies is proportional to the distance of the galaxy from Earth. And I'm specifically mentioning galaxies here because, well, that's what Hubble was looking at. But more importantly, I mean, we need objects that are outside of our own Milky Way. We don't want objects that have got a significant component of their motion, which is not just related to the expansion of the universe. Now, I know you don't have that purely in the case of galaxies. You know, galaxies are influenced by, forces between galaxies and such like. But it's not the same as being a star inside our own galaxy, and that star is then orbiting the center of the Milky Way just as we are. You've got extra components of motion there which are separate from the expansion of the universe. So this is why we're looking at galaxies with this. And when we're giving definitions of Hubble's law and describing Hubble's law and Hubble's constant, as often comes up in other questions, we specifically want to make reference to objects outside of our own galaxy when it comes to establishing this relationship. So that's the first thing. People are then happy enough with saying, okay, we've got a constant of proportionality, which is our Hubble constant. They are then fairly happy with the relationship between the age of the universe and the Hubble constant. You know, if everything started with a big bang, and that means everything was in the same point in space, the same singularity, if we've got some distance to a particular galaxy and some recessional velocity associated with that galaxy, we say, okay, well, how long ago would it have been that us as observers and that galaxy would be in the same point in space, which is going to be the distance divided by the velocity. So if we rearrange our equation from Hubble's law, then all we're saying then is the age, that time, the age of the universe, the time in the past that we would have been in the same location in space as the galaxy that we're observing, that age is 1 over the Hubble constant. So we can see that quite happily, and that is reflected in the seconds to the -1 in the Hubble constant. The confusion often comes in with the kilometers and the megaparsec to the -1. So let's deal with the first bit first then and take this age of the universe in years and get a Hubble constant just with the units of seconds to the -1. So that means that our age, we need to get into seconds. So we're going to take our 13.7 times 10 to the 9. Don't lose the point there. That's years. So we need to multiply by 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 and a quarter days in the year. Multiply all that together, so we're getting the age in seconds. This is coming out at 4.323, give or take, times 10 to the 17 seconds. Hubble constant, straightforward off of that, we just take the reciprocal, and that gives us our first value of 2.31 times 10 to the -18 seconds to the -1. Now we've got this issue of this kilometers per megaparsec. Now, there's a couple of things we can do to try and make that more understandable. So first of all, what do we mean when we're saying kilometers per megaparsec? So you can write it that way, but of course that is, as I've been saying, it's per megaparsec. If you were going to write that as a question, you could write it as how many kilometers for each megaparsec. That's one way of putting it. There are other ways of going about it, one of which I'll do in a minute. So how many kilometers for each megaparsec? Well, a megaparsec, they've told us, well, they've given us a parsec, so we need to multiply that by 10 to the 6. So that would be 3.09 times 10 to the 22 meters. That is our megaparsec. So that's the megaparsec. So how many kilometers in that? You divide by 10 to the 3, because we need to say how many meters in a kilometer. So we're just dividing that out. That is then giving us our 3.09 times 10 to the 19. So if we multiply that by our Hubble constant here, then we're going to get a new value of the Hubble constant. So we've got a 10 to the 19, 10 to the minus 18. So that leaves us with a 10. Our new Hubble constant is going to be 23.1 times 3.09, which comes out at 71.5. And now we've got these new units of kilometers per second per megaparsec. Now, if you're still not convinced, I'll just say one more thing and then go on to the second part of the question, and hopefully the combination of the two will then, make everything make sense. So let's talk about meters then. So a 1 megaparsec is equal to 3.09 times 10 to the 22 meters. I mean, that seems fair enough, doesn't it? So a meter then, 1 meter is going to be a megaparsec divided by 3.09 times 10 to the 22. Now, this is just rearranging that first statement. So if we want to do meters to the minus 1, so 1 over a meter is 3.09 times 10 to the 22 divided by a megaparsec. So this is what we're getting here. When we're changing something, if we could say that this first value here, this value here, 2.31 times 10 to the minus 18 seconds to the minus 1, we could write that as seconds to the minus 1, meters to the minus 1. Because, of course, meters to the minus 1 makes no difference. That just cancels out. We want to change a meters to the minus 1, this one here, to a megaparsec to the minus 1, which we've got there. We have to multiply by 3.09 times 10 to the 22. That's the scaling factor. We can see it in this relationship here. We can then do exactly the same thing for that meter there, and then turn that into kilometers. So we can say, well, okay, we've got 1 meter is equal to, 1,000 meters is equal to a kilometer. So if we want to change our meters to kilometers, which is what we're doing, we just want to make the meter unit the subject, we have to divide by 1,000, which is what I've done there. So that's why we're multiplying and dividing by the numbers that we are. Right, so that's another way of thinking of changing these units, both of which get us to this 71.5 kilometers per second per megaparsec. Right, let's see how the actual calculation helps in the second part of the question then. So the wavelength of the hydrogen alpha spectral line in the lab is 656 nanometers. Calculate the observed wavelength of the spectral line in the spectrum of a galaxy 50 megaparsecs away from the Earth. Right, so we've got our Doppler shift formula. The fractional change in the wavelength is equal to the velocity divided by the speed of light. So this is our recessional velocity of the galaxy. Now we can replace that with our Hubble equation up here. So we've got h0 times d divided by c. Now our units for h0, as has been said quite a lot already, is kilometers per second per megaparsec. So what we need to do on this to get something unitless, which is our delta lambda over lambda, this is our fractional change in the wavelength. So we need to multiply by megaparsecs, which is what we're doing. We're multiplying by 50, which is our D. So we've got 71.5 for our Hubble constant. We multiply by 50. So we're multiplying by a small number here. It's a very, very long way away, but we're not multiplying by 50 times 3.09 times 10 to the 22 to get the full distance in meters, because we've already taken that into account when we set up these units. We've already multiplied by the megaparsec bit. So now we're just saying, well, we got 50 of them. So we're multiplying by a much smaller number because the big number has already come in earlier on. So we're multiplying by that 50. Then we've got to divide by speed of light, but we want this in kilometers per second, not meters per second. So it's going to be 3 times 10 to the 5, not 3 times 10 to the 8. So we stick all of this in. That is then giving us a fractional change in our wavelength. So if we multiply this by our wavelength of the source, so we've got our change in wavelength in nanometers is going to be equal to 71.5 times 50 divided by 3 times 10 to the 5 multiplied by 656, because that will also be, it just keeps everything in nanometers. So you work all of this out, sticking it in the calculator, we get 7.817 nanometers. So that is 7.8 nanometers, the two significant figures. And this is a redshift. We know it's a redshift, so it's going to be a longer wavelength. So that means because we want to get the observed wavelength. So lambda observed is going to be 656 plus 7.8, which is equal to, well, 663.8. So 663.8, which we're really rounding all the way down to 660 nanometers to two significant figures. So I've gone through that in a lot more detail because, as I say, people do get confused by the Hubble constant. Mainly, I think, because of the second to the -1 and the megaparsec to the -1, because what it can look like is going on here is for seconds to the -1, we're dividing by this huge number, by this age of the universe in seconds. And then for megaparsecs to the -1, we're multiplying by a huge number. And that can seem confusing if you haven't thought through exactly what's going on. One of them, we're doing an actual calculation. The other one, we're doing a scaling of the units. So it's two different things that are happening. And if you really dig into this scaling of the units, either by thinking about it this way, so, putting it into a question, how many kilometers for each megaparsec, or thinking about it this way by doing more of a mathematical unit manipulation approach, it can seem odd. So hopefully I haven't laboured the point too much, but it's an important thing to get to grips with, because there are a lot of times where you have to do unit conversions and manipulations. So you really want to understand how these things are working. Right, that's taken up the whole sheet. So I'm going to clear the sheet for the next part of the question. And then we can go again. Right, so part B. Well, we got state what is meant by the Big Bang. Describe how it explains the origin of the microwave background radiation. Again, you're not having to go into massive detail on this. I think I've said this before on a similar question we had to this in part B before. So what is meant by the Big Bang? So we can say the Big Bang is the creation. Oh, the pen's gone funny. Is the creation of the universe. Creation of the universe. So yeah, you could say creation, origin, whatever, or the description of the origin of the universe, but you don't need a lot. We're just saying that the Big Bang is when the universe was created. So how does that explain the origin of the microwave background radiation? So let's go through some simple statements. So the early universe was very hot. Simple enough. And expansion, so this is something else that we're bringing in. So expansion of the universe led to cooling, and then the current temperature of the universe is, well, it's about 2.7 Kelvin. You can get away with 3 as long as you're somewhere in that order, sort of 2.5 to 3 Kelvin, you'll be fine. 2.7 Kelvin. So the universe as a black body, or modelled as a black body, I should probably say, modelled as a black body. Yeah, this is what we're doing with things like the displacement law. You know, when we're looking at the peak of, you know, where is the wavelength for a particular temperature where we have the peak intensity. So if you've got intensity against wavelength, then where does that peak occur? That's more or less what we're doing when we're saying universe modelled as a black body emits microwaves. If I can write it, microwaves at this temperature. This temperature equals 2.7 Kelvin. So there we go. So it's a simple chain. They don't expect an enormous amount here. You're just saying, right, the Big Bang is when the universe was created. It was very hot. It's expanded, cooled down, and at the current temperature of 2.7 Kelvin, this is associated with microwaves. So that's what we've got there. C, suggest how the microwave background radiation may evolve in the future. So you can just say, simply enough, the universe is expanding, therefore will cool further, therefore the wavelength of microwaves will increase. Microwave, okay, let's go microwave background radiation will increase. So again, another simple chain, which is more or less the chain that we had in the previous part of the question. So expansion, cooling, increase in wavelength. That's what we're getting here. So yeah, that was quite an involved question all in all, considering the detail went into on the first part of it. But yeah, certainly useful. Let's just do one more in this set then, just after 2 of them. Looks like a descriptive one. A star radiates energy produced from fusion reactions within its core. Explain what is meant by fusion and explain the conditions necessary for fusion to occur in the core of a star. Okay, so fusion is the joining together of lighter nuclei or separate nuclei. So you could say separate slash lighter nuclei into a single slash heavier nucleus. So that's covered what fusion is. So what are the necessary conditions then? So this needs, so we need high temperature, we need high density or pressure, or both density, pressure. We need, this is to overcome the electromagnetic or the electrostatic repulsion between nuclei. Between nuclei, so that they can get close enough for the short range strong nuclear force to take effect. Short range strong nuclear force to take effect and bind nuclei together. So yeah, you've got quite a lot you can say in that, but it's something that people are usually familiar with in terms of how fusion works. So you've got to put a lot of energy in to push these nuclei together because they're positively charged, but if you get them close enough, then strong nuclear force takes effect and they'll hold together. So that's covered. A, describe and explain the evolution of a star much more massive than our sun. Okay, again, we're doing this in steps. Don't need too many of these steps, but we've started off. So you've got, I'm going to do all this in shorthand, otherwise it will take forever, but obviously write this out in full when you're giving the answer. So start off, you get hydrogen to helium fusion in core. So that's the first thing that we've got. Then next, so that's one. Okay, don't write it out as a bulleted list, but you're just writing these out as separate self-contained sentences. So hydrogen to helium fusion in core. Then we can say this fusion slows, core contracts, temperature increases, and then we'll get hydrogen or helium fusion in a shell around core. So we're getting that, which means we then get, that leads to expansion. So this is taking us up to getting towards, red giant and red supergiant, red giant or supergiant. Yeah, we might get three sort of repeat process forming multiple shells, fusing heavier elements, multiple shells fusing heavier elements. So, and then you'll want to say something along the lines of up to iron in the core. That's as far as it can go in terms of fusing elements together. We can't go beyond iron. We're not getting any energy out. You have to put more energy in than you get out when you're fusing hydrogen. So it just doesn't, it's not a way of sustaining the star. Then eventually you're going to get a collapse, gravitational collapse, as fusion no longer is not enough fusion to sustain the star in a stable state. When fusion slows and star unstable, then we get supernova, and then we end up with either a neutron star or a black hole. So depending on how massive the star actually is. So I mean, there's other bits you could embellish in all of this, but that's the core of the story. That's the main elements. You've got these continual phases of something is being fused. You've got a sustained and stable state for the star when a particular element is being fused into heavier elements. That slows down. You get a contraction. The temperature increases because we're taking some of that gravitational potential energy. It's getting released in that contraction. That's increasing kinetic energy. It's increasing temperature. Reignites some fusion. That is then in these shells that are being formed around the core. Okay, the core, you can still get fusion going on in the core, but you're getting these multiple layers. So you need higher temperatures to fuse these elements. So if you're going to be forming the iron, that's happening in the core, and then you're getting lighter elements as you're moving outwards in these different shells. So this is all going to depend upon the mass. It's all going to depend upon the temperature, and you get these shells. Eventually, there's just not enough fusion going on. You're going to get a contraction where the increase in temperature is not sufficient to ignite enough new fusion to get a new stable period in the star's life. The star becomes unstable, the gravitational collapse continues, and then you get that rebound, that shock wave, which causes the supernova. You get a collapse and then a burst outwards of energy in this supernova because it's become so unstable. And the remnants after that, again, depending on what's remaining. If it's heavy enough that you're going to get at least a neutron star, this is going beyond the white dwarf outcome that you're getting for main sequence stars like the sun. we're collapsing down then through the electron degeneracy pressure down to neutron star, and then if the neutron degeneracy pressure is not sufficient, it will continue to collapse down to black hole. So you've got that whole story there. You don't have to remember every single element of it. You just need to get that that key story of stable, collapse, reignite, expand, collapse, reignite, expand. So it's going through those phases until eventually you get collapse and bang. That's what we're getting at the end of it, a collapse and a supernova. Right, okay, that ended up being two quite long questions, but useful ones in terms of understanding, I think.